Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome everybody to this session of Cloud Futures, our last session today. And it's my pleasure to introduce to you Alexandru Iosup, who is from the Delft University of Technology. He's going to talk to us on cloud computing support for massively social gaming. Thank you.
Okay, thank you for the introduction. So before I start with the actual speech, let me mention that this work is done in cooperation with a wonderful group of people from the University of Delft, from the Vrije University in Amsterdam, the Netherlands, from University of Innsbruck, Austria, and from Polytechnica University of Bucharest in Romania. And trying to postpone a bit more, delving into the subject, and I hope I will be given a few minutes to talk about this extra from the presentation. We've been asked to provide some tips on how we think cloud computing could help our work. Well, I'm a computer scientist, so I'm going to give you 2 tips on how I think that clouds could help computer science now. The first is, I think a service that would allow us to do heartbeat-based resource allocation would be great. And let me give you a sample scenario. We are doing now, during a project that we call BT World, we are trying to collect, observe global information about the complete BitTorrent network around the world. This is hundreds of millions of people sharing files in a very large file sharing network. The main characteristic of such a project is that you would like to get information continuously and you would preferably not miss anything. So of course we've got a nice data center, we've got some extra power. The problem is that at some point, parts of our city, the city of Delft, and in particular the complete campus of the university, just went into a blackout. So we experienced about a day of failure, that is, no data could be collected during this period. It would have been extremely helpful if we could have had a service of a cloud that, upon not receiving any kind of message from our servers, we are okay, we are running, could have started automatically the same service in the clouds. And definitely we would have been willing to pay extra just to have this kind of nice backup. Of course, we could have installed our own extra heartbeats that try to check the system, but our extra heartbeats, which actually existed, were in the same network. So we could not imagine that the whole campus would just go in a blackout and everything will go down. Okay, the second idea goes in the direction of dataset storage for computer science, or dataset storage in the cloud. We've heard about very large sizes of data sets that exist in other domains. Well, computer science also has quite large data sets, and here you can see a graph on which on the horizontal axis you see when different data sets were created for different communities, part of computer science, and on the vertical side you will see the different sizes of these data sets. And I'm talking about the Grid Workloads Archive, which is the largest collection of grid traces in the world. Established in 2006, it had just under 1 gigabyte of information. Then a year ago, we built the Failure Trace Archive, which stores resource availability information for a large number of distributed systems and contains about 10 gigabytes of information. We are currently building the peer-to-peer trace archive, so just consider peer-to-peer systems, about 20 or 30 of them, and then you take the traces. Then you start going into really large numbers of samples and large data, about 100 gigabytes. The gaming trace archive goes in the direction of 1 terabyte, and currently with the BT World project that I've just explained what it does, collects information from around the world for BitTorrent. We are collecting about 1 terabyte per year. We would definitely like to share this information with thousands of researchers. This is why we are building these archives. It's pretty difficult to actually maintain them. So the cloud could help with free storage, and I'm sure people would pay for processing such data sets in the cloud. Okay, so without postponing, I'm going to talk today a bit about what massively social games are. I'm going to present a bit our mission. It was very nice seeing so many slides with mission and goals and how we hope to achieve them and so forth. So it's nice that other presentations had such a slide. Well, we have two. So then I'm going to talk a bit about challenges for massively social gaming and how we can convert these challenges into opportunities for cloud computing. I'm going to give an example of what we did in practice to address these challenges, and talk a bit about our experience with the cloud for our applications and outside our applications. We did a lot of performance testing of clouds, and I will conclude. So massively social games are a popular growing market. Massively social games are a nice internet application with tens of millions of users. If you look on the graph on the left, and on the horizontal axis, you will see the growth of the number of subscribed players over time. You will see that this number of players is growing exponentially. Currently, the number of players that are subscribed, so really paying for the playing service, is around 25 million. But you have to consider that there are about 150 million that are actually active players, not all of them paying for this service. This makes the gaming industry on par with other entertainment industries such as music and video and movies. But what's in a name? What's a massively social game? Well, massively social games are online games with a massive number of players, so let's say over 100,000, for which social interaction actually helps or improves the gameplay experience. And in practice, they consist of three things. A virtual world. This is what the game actually simulates. In this virtual world, players can explore, do things, learn how to do things, or share experience. They can socialize, and more importantly, they can compete. There exists content, and game content can be of many different types. You can have graphical content, so different types of objects. You can have maps. Objects can be distributed around these maps to create an illusion of a real world. When you distribute objects across maps, you will probably try to add some semantical meaning to this distribution. And this is what puzzles actually mean. So there is some relationship between the objects and perhaps the way players interact with them. And players have to solve specific challenges related to these abstract relationships between objects. And this turns into more puzzles and chains of puzzles, which are actually quests. And there's also culture. So content is definitely a part of culture. And the third part is game analytics. So once we have a virtual world that operates and has a massive number of players, we have to make sure that this virtual world can operate safely and that it can continue operating and can continue developing. So with game analytics, you want to collect player stats and relationships and try to do something useful with this for the game. So now the famous mission slides. I hope I can read, because I definitely did not memorize these things. I have here a very small version of the slide. So our mission in terms of massively social gaming is to enable the development, deployment, and operation of massively social gaming for small businesses and for amateur game developers. Now, in terms of strategy, of course, we would like to be the first to identify various types of opportunities that occur in the context of massively social gaming. But the real strategy is to design and build fully fledged, fully working, cloud-based, massively social games. And while doing that, trying to uncover the real fundamental operations and way of running such nice applications. And we want, of course, to have a nice impact. So we would like to run multidisciplinary. Oh, thank you. Now I have a bigger version of the slide. We would want to have multidisciplinary and multi-institutional international teams with which to work on trying to achieve such an ambitious mission. And we would like to educate academics about the interesting world that is massively social gaming, and also use massively social gaming for academic education. We started around the end of 2009. Now about the cloud, I think it's pretty obvious what we would like to achieve. We would like to explore the capabilities of cloud computing to support real applications with massive social impact, and massively social gaming is such an application. I guess one of the main things that I would like to stress in our strategy is that we will try not to run out of hyperbole when describing cloud projects or cloud prospects before the clouds actually took a foothold on the market. So we've been hyping cloud already quite a lot. I think we are running out of hyperbole. One of the key parts of the strategy is also understanding the capabilities of the cloud paradigm by developing and deploying and running really real full-fledged applications. We started doing a bit of cloud computing research in early 2008, and we intensified this activity in 2009. So what are the challenges? Well, if you remember what goes inside the massively social game, that is a virtual world, some content, and then some idea of players that are somehow synthesized into analytics, then you can convert that easily into challenges. So what is the virtual world simulation challenge? Well, we know how to do simulations. The problem is how to do a simulation on such a platform as a cloud or on different types of platforms. What you would want from such a platform is the ability to scale very quickly. Let me give you a few figures. Reaching 1 million players in just a few days, reaching 10 million players in just a few months. These are the kind of target requirements that you would want to achieve. And if you think about the cloud, then I guess there's a clear match between massively social gaming and clouds. You can scale you want to scale very, very quickly and seamlessly. That's what clouds know how to do. Apparently, you can do this according to our research. Now, in terms of the content problem, what you would want to do is to generate automatically content for millions of players, completely automatically, again, on demand. So somehow this content has to be generated only when needed. You don't want to generate tons of content that is expensive if your players will not demand it or they will just quit the game. And you want the content to be balanced and diverse and fresh and meet the players' expectations and ensure some form of fairness in the competitive world that is a massively social game. So we've had some nice results with this as well. What I'm going to focus on today is the idea of solving the analytics problem of massively social gaming or massively multiplayer online gaming. That is analyzing the behavior of millions of players on time. And this kind of challenge raises questions in terms of data mining, in terms of data access rights, so security, authentication, in terms of how do you balance a trade-off between cost and accuracy. All these challenges match very, very closely what we've heard until now about what clouds can do and what we think that good research questions could be in terms of cloud applications. And for all the challenges that I've been mentioning so far, one of the key, let's say, requirements for actually having these challenges solved is to ensure that you can reduce the upfront cost of the specific solution and reduce the operational cost of the specific solution, and also keep the response times low and keep the system scalable. All these, I think, match very well what we are trying to do with clouds. So let me give you a practical example. Consider the subpart of game analytics where the analytics are performed by a third party. So you've got a game, you've got a population of tens of millions of players. What you want to do is to build smaller communities outside the, let's say, control of the game operator. And these smaller communities have hundreds of thousands of players that may require different things. For instance, they may want to learn what is their progress in the game. They may want to learn what is their group's progress in the game. They may want to find out whom should they play with so that they increase their chances of performing well in the game. They may want to get a sort of news digest of who played well in the game and how did that player do it. They may want to get automatically generated videos of how other players enjoy the game and play it. So what you want to do is to build a continuous analytics platform for massively social gaming in which the data are provided by a game operator but taken outside the game operator's platform and analyzed by a third party. And you want to analyze raw and derivative massively social gaming data such that important events are not lost. So you've got millions of users, You've got a dynamic size of relevant data. You've got different types of requests at different times of the day. You've got peaks of players that really join your community and try to get information about what happens. And you've got users with very different requirements. Some users would want to see only very simple types of information every week, some sort of summary of how they progressed in the game. They would not be willing to pay too much for this. Some other players really want interactive content, and they will be willing to pay for this. The only problem is that state-of-the-art third-party analysis only runs into the tens of thousands of players. What we did is that we built the Cameo framework for doing continuous analytics for massively social gaming. I guess the key part in this framework is that we are able and willing to use cloud, so on-demand, paid-for, guaranteed resources for sparse or excess load. And I will give you an example of what we managed to do with this Cameo framework. We took one of the major games on the market, Runescape. It currently holds the world record in terms of number of open accounts. So over 135 million players have opened accounts with this game. And we've collected a data set of over 3 million players, all the players that are recorded in the high score. So all the best players that remain in the game for long enough to become top players. If you remembered, one of the major problems with state-of-the-art analysis in terms of third-party continuous analytics for massively social gaming, we were talking about tens of thousands. Here we are talking already about a cloud-based application that was able to collect 3 million. So orders of magnitude more players, more information collected over a cloud. What this data collection enabled us to do was to also to investigate the level of achievement of different players. And we've observed that the number of mid and high-level players is pretty significant. What does this mean? Well, if you think of the traditional ways to generate content for games, then you will notice that most of the game content is generated for very beginner types of players. I'm not even going to talk about balanced content. I'm not going to talk about player customized content. I'm just going to talk about the level for which the content is addressed. The reason is very simple. It's difficult to generate content that really stresses the minds of the top players. This requires a lot of human input in the current solutions. So this allowed us to identify a new content generation challenge. How do you generate content automatically or not for mid and high-level players? I'm not going into more details about how we solved this challenge or addressed this challenge for small puzzles, but we have a nice paper on the topic. Another thing that you can get out of using this platform is the idea of cost. How much does it cost to do continuous analytics for a specific game? Well, this was one of the top largest games on the market, so it wasn't just any game, and it cost less than $500 per month. Now, game operators don't usually measure things in total cost, rather in cost per player per month. So you can see here a cost that I can't even pronounce. It has quite a few zeros. Let me give you another example of what you can do in terms of continuous analytics. We took the largest free online bridge community, which is bridge-based online. It has about 1 million players. What's nice about it is that top-ranked players, so real World Cup and professional players, join occasionally this network. We collected a data set of about 100,000 players. Okay. And thank you. And tried to investigate what are the social relationships between players. And in terms of bridge, a social relationship is formed between players that play together. Bridge is a game with 4 players paired together in 2 pairs of 2 players at a table. And this pairing relationship is something that gets built over time and becomes a real social relationship. One of the things that is a sort of constant around social networking around the world is that a social network of over 100 people cannot usually continue to function. It disintegrates into some sort of loose connectivity that doesn't continue. Well, we found that for this gaming social network, formed between about 9,000 players out of those 100,000, this large online social group can coordinate. So those players stuck to each other and continued to play. We were also able to investigate and identify different types of player behavior that are really beneficial for games. Okay. How about lessons learned about the clouds? Well, I think there are two main pictures of a cloud. On the left part of this slide, you will see, well, the path to abundance. So the cloud seen as really the path to success. You get on-demand capacity. It's cheap for short-term tasks. It's absolutely fantastic for web applications. It has great support for web crawls, especially through the elastic IPs. It has great database operations, great input-output. Everything seems perfect. But there is another darker reality, and this nice cloud can turn into a real tornado or a cyclone, as I happen to depict here. The problem is that the performance for scientific applications is absolutely awful. So you can check some results in our previous work. You will get, I don't know, 10, 15% of what you would expect out of a platform that you get if you would have this platform installed in your own department with the best possible setup, interconnections, and so forth. That's quite low. You don't have only this problem. You also have a problem of performance variability. So let's assume you start provisioning your cloud resources based on some assumption, so performance model. That one will change quite considerably over time. And you will get, okay, so let's keep the low performance for scientific computing. I guess there have been already 2 or 3 of the keynote speakers also mentioning very poor performance for scientific computing. What they didn't mention is this cloud performance variability. Here you see a tiny little sample of an investigation that we've done for all the different operations of all the different services provided by 2 types of clouds, the infrastructure as a service cloud, Amazon Web Services, and the platform as a service cloud, Google App Engine. And what we did is we really investigated what's the performance delivered every 2 minutes for a period of about a year and a half. Here you see the results for just one of the years in the middle of the sampling interval. And what you will see most noticeably is that the median performance fluctuates quite a lot. This is the median performance for one of the operations in terms of transferring data. I'm not even going to talk about the outliers and other statistical properties that show that this particular operation has variable performance. If over the year the performance varies quite a lot, the median performance varies quite a lot, then you've got to do something about the cloud provisioning process. Okay, so to conclude, massively social games are a million user, well, I would say even 100 million user, multi-billion, perhaps even tens of billions now market. Such games consist of content, world simulation, and analytics. The current technology involves upfront payment, cost and scalability problems, and most importantly, it makes players unhappy. This is mostly related with delays in the world simulation and with the quality of the current content, which both I can argue, and if you ask me, I will try to argue about it, are based on the analytics part. Our vision is that scalability and automation can be achieved by integrating massively social gaming into clouds. Our ongoing work has different frameworks and platform improvements for reaching this vision. And I think we can achieve a future in which happy players are matched with happy cloud operators. So this is it. Thank you.
Thank you very much. We have questions? Yes, over here.
So about the bad performance that you observe, are you constantly monitoring this? And have you commented on these performance problems with, let's say, the providers, and what was their response?
Yes, so the short answer is yes, we are constantly monitoring this. We are actually using 2 different data sources, so we are not measuring ourselves continuously, or we haven't done this for the past 3 years. We use the cloud status data, and we use the data published by the cloud providers themselves. as to what causes this performance, I guess, well, the cloud providers themselves told you in their presentations a bit ago. That basically, well, in terms of the type of performance that you're getting, the platform itself is not designed for those types of workloads. And I think one of the presenters, Microsoft Azure, really showed that, for instance, the network interconnects were partially to be blamed. There are other performance problems. I'm not sure that answers every part of the performance issue. And in terms of performance variability and variation over time, over long periods of time, well, these systems are really under development. Also, their own operators recognize that the systems are under development. So, yeah, I would expect changes. But this is, in a sense, bad news for somebody who would think that, okay, you know, we can take the platform and really use it long term. Or just try to provision the capacity on the spot. That might not be easy to do. You may want to run a bit, understand what's the current performance in the network or in the cloud, and then do something about it.
Other questions? Yes, one more here.
In terms of characterization of the kind of, you know, like in terms of game analytics that you talked about, so is there a good sense of what sort of computations? I mean, is it you said something that is a massively large online gaming, but is it the sense of, I mean, is it running a set of sequential tasks or in parallel, or is there lots of synchronization involved? Can you give us some characterization of the computation?
So definitely you will have different tasks that have to synchronize in terms of data collection. So unlike other data processing sequences, you definitely need to collect your own data. This changes quite a lot the game. You can do a lot of optimizations in terms of what you can collect and compute versus only what you can compute. In terms of what kind of computation, many of the computations, especially those going in the social network analysis part, exceed the capacity of one machine. So those ones will need to run across different machines and be synchronized. In terms of other types of operations, many of the things you will want to do in a sense of a sequence, of a bag of tasks, large-scale sequence of tasks. So you will want, for instance, to do the same analysis for a large number of players, and how you're actually splitting the job, whether it's a single task processing multiple players, but then having a large number of tasks, or a single task doing this, yeah, depends a bit on the type of computation.
Yeah. I mean, you can flip the question other way around, right? I mean, in terms of, you only said, you know, what clouds provide in terms of performance. So in terms of programming abstractions, right? So do because these games paradigm, does it require you to now think a fundamentally new way of programming paradigms?
Okay, well, I think we better get the answer for that offline. Okay. Sounds an interesting question.
Just when I was trying to get...
Okay, well, thank you very, very much. Okay.
The mic.
Oh.
Great paper. And now we have
He has a mic, so.
our next speaker, but we're going to get hooked up first. Okay, so it's my great pleasure now to introduce as our second speaker Bertrand Meyer from ETH Zurich. And he probably needs no introduction, except I must say one thing, that he is an absolute expert on using the tablet PC, as you are going to see in his talk today.
Well, actually, I think I'm the only person in the world to, I mean, someone has to use this great Microsoft technology, so I feel kind of, well, actually it's great. I don't understand why not everyone else is using it. So I'm going to talk about the last commit and the end of configuration management. I hate configuration management. I think it's bane and a shame, and we should replace it by something better. So the more general talk is about a tool that we've developed, which I should mention who is we. The prime mover behind this effort is Martin Nodio, Dr. Martin Nodio. I think he got his PhD certificates yesterday or something like that at ETH. And he's been developing this as a kind of skunkworks project with the help of a master's student at Hanoi University of Technology who is collaborating with us as part of a project, or of a course project actually, that I'll mention briefly at the end. So what they've built is a cloud-based integrated development environment, IDE, so a software development environment, which is a version of our Eiffel Studio development environment, and it makes it possible to have a shared repository for a software project. And of course, the most important part is code, but really when we're talking about software and artifacts, it's more than code. It's code, it's designs, it's analysis documents, everything that a software project might need. It allows direct manipulation by all project members, developers as well as managers, and it allows unobtrusive configuration management. I'm going to explain what I mean by this, but in fact we did not invent anything. We just applied techniques that are now prevalent, ubiquitous, thanks to tools like Wikipedia, for example, or Google Doc. So the first point about configuration management is that I should make full disclosure, and I hope you appreciate the discretion of the plug for my latest book. This is a great book, and I hope you all rush and buy it. And it's my introductory programming textbook, which is based on several years of teaching introductory programming at ETH. There's a software engineering introduction, a chapter at the end, which is an introduction beyond programming to software engineering, and it raves about configuration management, saying this is one of the most important things that students can remember, can learn. Configuration management is one of the principal best practices of modern software engineering, which every project, large or small, should apply. So now I know this is being recorded, but I have to make a public confession. This is my outing. I don't practice what I preach. I hate configuration management. Actually, I hate the tools. I've tried all of them. You know, I've tried Windows SVN, whatever it's called. I've tried to use Eclipse to do configuration management. I tried Tortoise. It's a catastrophe. It never works for me. So it's kind of a running joke in my group that I send an email to an assistant, and he checks in the stuff into the configuration management database. And partly it's my fault, but I don't think it's entirely my fault, because after all, I am a techie. I like tools and I can learn tools, but this is just too much, how can I describe it, 20th century. So this 20th century configuration management process, which of course quite seriously is very important, and of course what I'm going to argue is for better configuration management techniques. I've also seen people, students for example, who say we don't need those stupid configuration management, and you can imagine what the results are, right? So let's put this in context. But the problem with configuration management as it's practiced today is that you have this kind of process where you take some software artifact, it's called an update or checkout, then you start working on it very hard, and so that, edit, let's say in a broad sense, then you check it back. So it looks nice when you see it like this, except that, of course, in the meantime, you have 10 of your colleagues who have also done some updates and commits, and then it's a total mess. You have to reconcile their changes and yours, and this is really the bane of practical software development. And there is a better way, okay? There is a better way, which, without too much fanfare, has been introduced in the past 10 years, 10, 15 years or so, in which we all now apply. So one example of this is Google Doc. Provocation has its limits, so I'm not going to use Google Docs here. I'm going to use Wiki. So so let's see. Let's do some search. I heard there's this guy who has a Wikipedia. Oh no, it's doing this to me again. No, I logged in 2 minutes ago. Okay, this doesn't count in my 20 minutes. USMS guest. This doesn't count in my 20 minutes. USMS guest. And then J. Okay, well, I'm not responsible for this page, although now I'm going to be. So let's see, edit. Edit this page. And when was the guy born? Well, okay, let's say 2010. now, because this is very dangerous, right? I'm hacking Wikipedia in full view of everyone and in Microsoft premises using Microsoft's network. This is going to get you into trouble, Judith, I think. Well, illustrating. Okay. And that's it. I was born in 2010, right? Well, okay. There's a history page. Okay, let's correct this. So this is my configuration management, right? Every time I make a change, there's my guardian angel who, now I pity the kind of 2 million people who are looking me up, you know, right now. As this is going to be really a shock for them, but I hope they'll recover. So I'll go back. I'll go back to this page, and I say edit again. Where is it? I lost it. Yeah, edit this page. Yeah, and now. Yeah, and now I'm editing it, and I should leave some trace so that it's not okay, and it's back, I guess, to my real birth date, which I hate to admit, but it is correct. So this is configuration management as it should be, right? You just do things, you just do your thing, you change, and of course you mess up because we all mess up. And then if you need to go back to a previous version, well, you realize that you have had your guardian angel watching over you and keeping track of what you're doing. And there's really no reason we should have this prehistoric, medieval approach of checking out, working and checking in. Okay? So that is the form of configuration management that we should be using, and not just for things like Wikipedia or Google Docs. Now, more generally, the picture that we have today, if we are a programmer of software development, and here I'm coming to the core of the presentation, if you like, and Ed Lazowska gave an excellent introduction or an excellent setup for this talk yesterday when he said at the end of his talk that software development is the ultimate application of cloud computing, approximate, but I think quite close to. So that's where we're going. So today we're not using cloud computing. In fact, I also have this running live here. This is CloudStudio, right? It's my project, and I'm developing it. And of course, if I'm using a configuration management system, at some point through the environment, through some hook in the environment or outside of the environment, I'm going to commit my changes, and then of course, as in the previous scheme, I'm going to have to reconcile them with those of anyone who might be working on the same elements. So it's CloudStudio, it could be Eclipse, it could be Visual Studio, except that it wouldn't be as nice, but the concepts are applicable to any modern development environment. Now, the reality of software development is that it's more like this, right? There's a customer somewhere, there's a requirements team somewhere else, then some part of the development in Bangalore or Shanghai, and some part in somewhere else, and they all need to work on the same base. That is the development, that is the context. And in fact, I took this picture by just hacking a real picture, which is the development team for Eiffel Studio, partly academic but mostly in industry for Eiffel Software. So this is our team, right? Santa Barbara, Florida, France, Zurich, Moscow, and Shanghai. The times are those at which we have our weekly meeting, right? You can imagine the difficulty. I mean, I insist very much on having a weekly meeting, 1 hour, but just finding the common time is not that easy. The point more directly relevant to this particular discussion, however, is that there are all kinds of people, all kinds of locations where people are working on the same project, and this is the rule today. Maybe not as many sites as we do, but it's very common both in commercial developments and in open source developments. And we need IDEs that are devised specifically for this kind of development. And today's IDEs are not. The issues, of course, are many and difficult. For the programmer, I need to make sure as a programmer that I use the correct version of everyone else's modules, correct in the sense of the latest one. There is nothing worse than working to an API and then realizing that it's not the right one. I don't want to step on someone else's toes, and I don't want them to step on my toes. I want to know what others are doing at all times. Now, if I'm a manager, I want to get a true picture of the development state. This is one of the most difficult issues today. Because people may have checked out a piece of code and they might keep it checked out for a week, for 2 weeks. So you look at what you have in the repository and it does not give you, the manager, the correct picture of what's there. You really want something much more accurate and instantaneous. You want to allow different developers to work concurrently on the same software elements with some precautions. We want to make sure that everyone uses the same version of the base modules, the one that are supposed to be baselined and fixed and completed. You want to avoid regression errors, which are terrible. We want to be able to recreate at any time any previous version of the system because some customer might want it, or you want to be able to reproduce a bug. And then for both programmers and managers, we want to avoid configuration errors, which are a waste of time. We want to avoid conflicts in new modules. And of course, I think most of us would like to produce reliable software, unless maybe we are hoping for a good maintenance contract. But that's a side point. So from this view of today, what we're trying to provide with CloudStudio is a different view, where we have a cloud-based solution where all developers, to which rather all developers can refer, and which allows everyone to work on the same base. So here's a little demo. No, sorry, this is. Now I hope it hasn't again logged me out. Okay, so this is CloudStudio. I'm going to log in. So it's cloudstudio.ethz.ch. Okay, I have a number of projects. So the point is not that it's particularly fancy or powerful. The point is that it's going to look reasonably like Eiffel Studio. So I'm going to open this project. At least that's what Martin told me I should do for the demo. And I'm going to change something. Actually, if I may. So of course the demo effect is. Oh yeah, okay. So I'm not going to do something very powerful, but let's replace 50 by 60. It's about as courageous as I am. You know, live demos are usually not a very good idea in talks. And it starts a compilation. And yeah, it has parsed the whole thing. And well, yeah, I could also introduce an error, you know, yeah. So basically, I can do what I would do with the normal version of Eiffel Studio, the normal meaning non-distributed version of Eiffel Studio. So here I've introduced an error. So you see the idea. It's a very simple idea, right? It's like Google Docs for software development in a way. So the principles are: there's a shared repository of a software project. I mentioned this already. Direct manipulation by project members. You know, direct manipulation in the core sense of direct manipulation, as introduced by Ben Schneiderman many years ago. What you see is what you get. What you work on is the actual project. It could be nothing prevents you from making a local copy, but you should not, as a rule. The manager gets an instantaneous, accurate picture of the state of the development, and unobtrusive configuration management. That is to say, you don't do commits or updates. You just do your thing. You know, if you're a programmer, what you want to do is to program, and to make changes, and then you want to have someone watch over you. The comment about methodology, this is very recent stuff for me. Obviously, many people have known about this for a long time. I really discovered it fairly recently, and I think it's very interesting. There's a move from review to commit. Review then commit to commit then review. There are some interesting articles, thanks, in the literature, in particular about Apache and how around 1998, I think, or a little later, they moved from RTC, review then commit, to CTR, commit then review. That is to say, for those of you who know, for example, things like software transaction management, right? It's the same idea, except it's applied to people rather than software. You do your thing, and then you check that it's okay. There's this old saying, or at least it's very popular in this country, that it's easier to apologize than to ask for permission. Well, that's exactly the point, and it's a fairly general tendency in software development today. It's a general trend, right, which you can see in many different areas of software engineering. And we are transitioning to this at Eiffel Software. However, what we see missing in other approaches is tools, because you want to know, for example, as a manager, what has been committed but not reviewed. You want to know what has been committed and reviewed negatively, things like this. So you need a very strong tool infrastructure, and CloudStudio, I have to justify my use of a tablet PC at last. I know that's great, but this is what you came for, and you have been waiting for me to draw something on the screen, so finally I've vindicated Judith's comment. CloudStudio, a cloud-based environment, is the ideal context for such tools that enable communication. So configuration management is going to be the way I described it. No need for explicit update and commit. By default, changes are immediately reflected on the shared repository. What does immediately mean? By default, it's a successful compile. Okay? This can be parameterized. The conflict detection is optimistic. That is to say, you let the conflict happen, and then you as early as possible, fail fast, provide a mechanism for reconciliation. The history is managed automatically, and of course you can go back to any earlier version. You can define explicit name versions, so you can still do a commit, but a commit simply means next time I compile, this is going to be version 6.2. That's what a commit means. There's nothing more explicit than that, but of course you want to be able once in a while to give a name. One of the problems with the Google Doc scheme is that the granularity, if you have looked at it, if you have used it, you will have noticed that the granularity is far too small. Every time you add a comma, there's a new version, so that needs to be improved. So we have many challenges still facing us. We want to make sure that we have the same performance as with the local version, and the performance, of course, has been a recurring theme in this workshop. We want to provide the same level of user interface quality as the traditional version, and of course, we are basically like anyone else relying on JavaScript and its stuff, but we think we can achieve it. We want to support branching. We want to find the right level of granularity. We want to enforce the disciplines through management tools. Something that is very important is that we want to have a kind of global environment, right, including communication. So we want to be able to introduce, I'm sorry, I'd love to be able to cite Microsoft technologies here, but I'm going to cite Skype. Okay, we'd like to kind of package Skype or WebEx, this kind of tool within the environment without reinventing it, because communication is fundamental to software development. And we want to apply this to teaching, so this is an occasion for another plug. Our course, Distributed and Outsourced Software Engineering, this is a course that we teach in which the project is done in cooperation by students in many different universities. And actually, this is where this student from Hanoi came into the picture. Hanoi University of Technology is participating in this course, so the students work in teams that have 2 students from one place and 2 students from another place, typically, which is an exciting experience for everyone. The general context, I'm almost done. The general context, just to preach a little bit to finish, is this fundamental idea of seamless development, which is actually illustrated here by, Eiffel Studio. This idea that you don't have an analysis tool and an IDE. It's all together. You can go back and forth between text and graphics, and more generally, we want to have everything together: analysis, design, implementation, maintenance, verification, project management, and computation. And communication. I think I don't have time to go into this. And as a summary, it's probably the first time in my life I finish a talk on time, although I still haven't finished it, so I should wait before I boast. Ed Lesovska said on Thursday that software development is the ultimate cloud application, and I think he's right. And I'm very surprised that we as a community have not seen this yet, have not done more in this area. So we are proud to be going among the first, I think, into this area. I think this is the way people are going to develop in the future. Our approach tries to leverage the cloud to provide a modern cloud-based integrated development environment, and really commit and update are for your dog if you don't like your dog. Thank you very much.
So, questions at the back there.
Are you using the cloud for compilation as well as for storing the programs?
At the moment, yes. But yeah, this is still, as you've probably guessed, it's still in its early stages. So we might develop more savvy strategies for moving between, doing more on the client side. But at the moment, we're just playing the cloud game fully and doing everything on the server.
Well, I was hoping actually that you're doing it there.
Yeah.
Okay, yeah.
And like Wikipedia, branching can be very useful in software development. So you said that you don't support it yet, but you are working on it?
Right. So branching, branching is something. I mean, you know, if branching could be removed from the human experience, I think the human race would be happier. So the short answer is I don't know. I mean, the good news is that it was on there's a comment which was on a slide which I didn't mention, which is that this is all, after all, a layer on top of traditional configuration management systems. In our case, at the moment, Subversion. So anything that you could do before, you can still do, right? And that's about the only answer I'm able to give. I'd like to know how to handle branching. Branching is a tragedy. You know, and if we could avoid it, it would be much better. So the short answer is you can do branching, but the way we've been doing branching for ages, and we don't have any new ideas there.
Alexandru?
So I admit openly that I don't know many things about software development, but it seems to me that you're assuming that the developers are all of equal skill and of equal styles of programming. Do you think that there is an impact if the programmers have very different styles? One would prefer working on bigger chunks of code versus the others, and if so, what happens? And the other part of the question is what happens if the coders are of really different skill?
Yeah, that's a very good question. We haven't devoted that, so I think you're wrong. You do know a lot about software development. So we have not explored this issue very much. I think what we need to do is to build into the tools ideas that have turned out to be extremely successful, in particular in open source developments. So it's clear that in successful open source projects, you have a number of concentric circles, so to speak, with the most novice developers at the outset, at the outermost level, and then, you know, the Linus Torvalds of this world, or Eric Gammas at the center. And so at the moment, we have not built anything of this kind into the tool, because we're working on the assumption indeed of teams like ours at Eiffel Software, which are of the peer kind that you're describing, and similar teams in customer organizations. So on the one hand, we need to develop some mechanism to support what you're describing. On the other hand, I would like to keep such mechanisms relatively light, because I believe very much, and I'm a new convert to this, I must admit, in this trend that I described of, you know, it's mess up then apologize, you know, or fail first, which is really the same thing. I think with a little bit of boldness, as long as you're not directly changing, say, the running version of the flight control system of the United States, you know, it has some limits. Within reasonable boundaries, this idea of let people be creative, and then if they mess up, they'll have to pay the price for it. I think it has a lot to say for it.
Yes, at the back, yeah.
Short questions. First is, has this move from the server to the cloud made any difference to the users in terms of the methodology?
It's too early to tell. But I think I answered this partly by mentioning the methodological assumptions and implications behind this model.
So it doesn't mean that the user still is seeking a very transparent move to the cloud, moving to the cloud.
Yeah, but the main methodological implication, I think, and I think that is the answer to your question, is this general style of letting people be bold and correcting errors after the fact, rather than putting in all kinds of barriers. You know, it's like Wikipedia. Think of when we I don't know about you. The first time I heard about Wikipedia, this idea that anyone can edit the entry on George Washington from an internet cafe in Bangkok. I thought this is crazy. It's not going to work, and in fact, it does work to some extent. So it's kind of the same general trend here of saying, well, there's going to be mix-ups, there's going to be problems, but in the end, things will kind of work out.
So the second short question is, how do you handle conflict resolutions at the design level, especially when you have collaborative teams working around the world?
I think the answer does not fit in the time that's imparted to me.
All right. Well, we'll take one more question. Was there one?
So can I have the third one?
Yeah, go for it.
So how does it compare to JAS from IBM?
It's much lighter. Well, two things. It's much lighter, and also it integrates everything. It's really the development environment. It's not just the communication and management environment.
Collaborative application lifecycle management and all that. So this
Okay, describe it for you can describe it as jazz for the rest of us, right? For the poor among us. But more fundamentally, I think it's really the main distinction is the close integration of absolutely everything into a single ID. You know, there's general trend in the evolution of software engineering of adding tools and of saying that management is key. And this is the response of the hacker, saying programming is what matters most. So let's take a programming environment and make it handle everything, as opposed to come more to the more top-down approach.
Okay, well, let's thank Bertrand very much.
Thanks.
And our next speaker is Karin. Okay, so it's my great pleasure to introduce in the last session here today, Karin Breitman from PUC-Rio and friends, and they're going to be talking to us on cloud TV. That would have been an easy one to remember. Thank you, Karin.
Hi, thank you everyone for staying with us until the last session of today. So our agenda for today is a little bit tight, so we're going to talk about the complete disintegration of TV and why we think television is going to die in the next few years, why the cloud is going to be able to catch everything, and we're going to show you, squeeze two different architectures that will deal with these different problems in the cloud, and why those are killer applications. Well, we'll wrap it up in the end, and well, each one of the boys will show you one of the applications. Then I'll come back and I'll talk to you about this as essentially being cloud research, what we're doing today, architectures, what we're putting in. And I'll wrap it up with a very quick thought of what, because the event is Cloud Futures, so what's going to be the future of all that, what we're going to be doing, or I think we're going to be doing the next 5 years. So because we're doing it very quickly, so I just invite you, everyone who's interested in the topic, just go to computer. Jim has put out a beautiful issue this April all about cloud, and we feature one of the articles describing exactly what we're doing. But back to TV. Well, TV started in the 50s as a very static model. We had the whole family sitting around the TV set watching it, and we had very distinct roles. On the top, we had the producers who would produce the shows, Johnny Carson, for instance, that were distributed to broadcasters that were responsible for making that being aired until it got to your homes, and consumers just sat down there, enjoy their Sunday night TV and watch that. Well, this changed radically as you've been to Dan Reed's talk this morning, I'm sure, and he talked about, you know, how many computers do we have? I don't think it's about computers, but rather it's about displays. So we started with the movies, then moved to PC, to the TV that were, you know, inside our own private spaces, and then to PCs. But now we live in an era where we own private displays. We all do. I have 4 in my backpack over there. I see many people with computers. You have, I'm sure you have cellable phones and God knows what else, right? We're running this presentation from a display that it's not even a computer. What is it? So this is ruling, and this imposes a huge amount of work to what we have as TV, because it all crumbled down. We don't have TV now. Our TV connects to the internet, and the internet, on my computers, I can watch TV, and I can watch TVs on that, and I can watch TVs on my mobile phone. And we have to process all this information to a gazillion different formats. So what's going on today is that we just mingled everything. So whoever was producing software now can distribute and has to distribute to dozens, and I mean dozens. We've been talking about biodiversity in computer science all through the week. But what about the biodiversity in mobile devices we have here? iPhones, Nokia phones, Motorola phones, all sorts of different computers and stuff. So we have to produce media and transcode this media to all of these formats. And this is what Rafael is going to talk about, our killer solution for this and why the cloud has to be used to process this to this myriad of formats. Then on the other side, you have to distribute it to consumers. And now consumers are producing media. I'm sure everybody saw Haiti coverage. We turn on the news, and there's more and more and more video, user-generated content that was produced by people and submitted to the networks. But how much of that can we take? How much of that can we process and receive and see? So we need a lot of computational power to deal with it. So, well, we'll just begin by showing you the two architectures.
So before we start talking about the split and merge, this architecture for distributed video encoding, I think that's important to understand why do we need to compress video and why this task is so complex. So if we take, for example, 4 or 5 minutes of full HD video, raw video with this profile, we would take 177 megabits per second of data rate. And it's not possible to deliver this content over the internet with the current user connection. If I want to get access to this content through my cell phone, through a 3G network, I just can't do it because it's too high. So we need to reduce this data rate, and to do this, we need to remove some redundancy, such as temporal or spatial. So here's a diagram of a video compression, basically a video compression process, and it's just to show you that it's quite complex. There is a lot of math that we need to do, and for each frame, we need to do a lot of operations. And in a video with, for example, 30, 40 frames per second, that's a lot of information to process. And if we have some cases such as breaking news, we don't have time we need to process this content very fast. So we need to reduce this processing time to make this content available as fast as we can. And basically, when we deal with huge data sets, I think that the MapReduce is the most popular paradigm for parallel processing. And it's very good for some applications, but in the specific case of video processing, it does not fit very well because there's a lot of for video, for example, we have different algorithms that we need to use for video processing and audio processing. There's a lot of correlations between subsequent frames. So the MapReduce is not the best choice to do this parallel and distributed processing of video. So what we propose is a split and process and merge architecture where we get the original video, split it in several chunks, split the audio stream also, and then we process all these chunks and the audio in a distributed environment parallelly. And then we merge the results of this processing to get the full encoded video. And to do this split, process, and merge, basically for the split, we need to split the video in several chunks with several with a specific frame and specific quantity of frames. And basically, we do not break the file. In this case, we are using a time shifting technique that we just mark the chunk start and the end. And it's very good because we don't need to rewrite the container of the video. One important remark is that the chunk size must be always greater than the GOP, that is group of pictures, that is the interval between the keyframes. If the chunk size is smaller than the group of pictures, we will lose the compression efficiency because we will insert a keyframe where it's not necessary. And we can use decision-making algorithms to help us to discover the optimal chunking size. For the process, basically what we do is the video compression itself and the audio in an independent way. And it's important to allow us to choose between different encoding profiles and techniques. For example, I need to generate video for web, and then I will use a specific data rate, or for mobile networks, I will use a lower bit rate. So it's important to have the possibility to choose between different encoding profiles. And one important thing that we need to take care is the dynamic resource provision in the cloud. So once I have a different duration content, so we need to, we will have different quantity of frame or of chunks. So we can just scale up or down our architecture, adding or removing nodes to do this dynamic resource provisioning, and then process all chunks in a simultaneous way. And finally, we have to merge the content. So we need to reorder all video chunks and then merge it. And finally, we do the audio merge with full encoded video and do the audio remixing. And finally, we rewrite the file container. So if we want to deploy this architecture in Amazon, for example, using the Amazon Web Services platform, it looks like this. We will have several EC2 instances for example, our worker and master nodes. We can use the S3 for content storage and the relational database service for state persistency. We're also using the Cloud Crowd, which is a Ruby framework for parallel and distributed task processing. And after some tests, we got this result. And basically what we can see is that it's a comparison between the traditional process and the split and merge architecture. And we can see as the content duration increases using the traditional process, the total encoding duration also increases. And it's not good because if you have, for example, if you want to deliver on the internet the Super Bowl game, it will take a very long time using the traditional process. So it's not too good. And using the split and merge, we have an almost constant encoding duration. And we can do this just adding more worker nodes in the architecture. So let's do a simple cost analysis of if I want to use the Amazon platform, how much does it cost for us? For example, if I want to produce 500 minutes of video in a single day. So the first step, I need to submit the source file, for example, a DV 25 megabits per second to EC2, and it will cost something around $10. Then I need to encode all the content, send it to S3, store the source video and encoded video in the S3, and then get the encoded video back. In the end of this process, we will spend around $60 a day and $20,000 a year, which is cheaper than a single server. And we can produce all the Super Bowl match in 2 minutes against the 12 hours from the traditional process and just for $1. And we can reduce it if you use a spot request from Amazon, you can reduce it to less than 50 cents. So Marcelo will show you now an architecture for submission systems.
So what I'm talking about now, I'm going to describe another architecture leveraging the cloud computing for open submission systems. One of the things that Karin was talking was the popularization on photo and video cameras. A lot of content is being produced by users, what is called the user-generated content, and being sent to the internet, where media conglomerates can use that, or even new websites as YouTube, which have a huge audience and a huge lot of content. Usually, it's very hard to estimate how many content you're going to receive in a system like this. So it's really a guesstimation. You don't usually know how many users will like the service and if it will be on how much infrastructure will be needed. That is really an advantage where cloud computing can help you solve this kind of infrastructure problems. So the proposing systems were actually used in a real project in Big Brother Brazil, which is a reality show that's run in Brazil. Just as a disclaimer, Rafael and I work also at Global.com, which is a media conglomerate in Brazil. Global has the ownership of the Big Brother reality show in Brazil. It's a huge success in Brazil. Don't ask me why. We have an audience of 80 million simultaneous people watching the TV show on Open TV. And we have, and the internet has a very relationship with the TV show on the TV network, because users have to vote which, for the ones who doesn't know how the reality show works, 16 random people are selected to stay in a house for 3 months without any contact for the outside world. And every week, one of the guys get out of the house. And the selection process of who's going out of the house is done in the internet on our website. Before the reality show begins, we have a selection process that users have to apply to be in the reality show. Don't ask me why. I don't know why so many people want to be in the reality show, maybe to be in the television. But we receive a lot of applications. And we decided to move the process of receiving. We use it to receive videotapes using snail mail, and then we decided to move to receive videos using the internet. First, we thought of using YouTube or Vimeo or other video site, but we had a lot of problems with copyrighted content. We needed to have the copyrighted the rights, exclusive rights for these videos. So we had to develop this infrastructure by ourselves. So the first big problem was, how many videos are we going to receive? We used to receive 20,000 and 30,000 by snail mail. If we opened that for the internet, we didn't have a clue on how much videos we would receive. So using the cloud would allow us to focus on solving the problem without needing to worry with infrastructure. So for instance, this is the website that we use to receive the videos. Basically, the user had to fill a form and upload the content. So the basic infrastructure, what we would need, we would store the user information on a MySQL, on a database. For instance, we use a MySQL. We had to store the videos on a storage, and we did a lot of service because we received videos in a very different kinds of formats and codecs, and we have to transcode all these videos to a standard format, so that they could be watched by the production team of the program, of the reality show. So what we've done is we just replaced the storage, the local storage and the local transcoding farm for a cloud solution. For instance, we used Amazon Web Service. Right now that we have the Azure tokens, we can use Azure Service as well. So basically, we have a local system that will send the video files to a storage system, for instance, S3. The EC2 instance will do all the transcoding, and we use SKS to queue which kind of jobs need to be done for these systems specifically. The transcoding command line that will be run on the cloud, and then when we have all the videos transcoded, we can offer it to the content to the producers of the program to select which candidates will be selected. So what we've got, just to show, we didn't need to worry with upfront investment on how it would scale. We wouldn't need to worry on how many servers would be needed to buy or the administration of all this infrastructure. And the cost is pretty low. For 100,000 videos, it would cost $500. And so if you do the math, that's less than 1 cent for a video, and you don't have the upfront payment, and you don't have, in Brazil, when you buy new servers, you have to import them. They take almost 40 days to ship to Brazil, so it takes you a huge time not only to plan the infrastructure, but even to buy and to plan that. So it was really a very interesting case what cloud computing could leverage this project and stop us worrying the size of the infrastructure that we needed.
Okay, so we very quickly showed a couple of cloud applications and things that we're doing today. What we have today in the landscape is the following. You have, from one side, we have cloud producers. They're doing cloud infrastructures like Microsoft Azure, like Rackspace, and on the other side, we have people who want to use the cloud. But hell, it is difficult. It is really difficult. You think configuration management is difficult? Try to see what these guys are doing with, terminal. It's really hard to set up. So research today, and what we've seen the last 2 days, is just trying to bridge through this. But now to wrap it up, I'm a software engineer, and this is research we're doing. This is going to be good for the next 5 years. We need to provide these guys to provide solutions and make cloud solutions work. But we have to think, and if that we can give, we're researchers and we can give some insight, is what's going to happen in 5 years? Well, in 5 years, this is going to blow. This is a cloud bubble in the sense that, people will start to forget how much money they saved by using the cloud and start thinking like, I don't want architectures. I don't want to rewrite my code to go to the cloud. I don't want to, this is error prone. This generates a lot of overhead. Why can't I generate cloud systems to begin with? Why can't I think about cloud systems earlier on? Why don't I think about them with requirements, and why don't I think about the models that I need to develop these systems? And I have to go back to things and to principles in software engineering, like things that Barry Beam said, it's more expensive if you treat bugs later on. And just doing that at architecture level will not do. We have to do it before. And this is what real research is all about. And this is what we software engineers have to be thinking about and doing in terms of cloud. And, well, if the cloud is going to be 1/10 of what it's cooked up to be, this is the grand challenge for software engineering. We have to have a hands-on. We have to call everybody. We have to go and say, Barry, come on, work with us. Come on, Caper Jones, let's get the guys from Atlantic Guild Systems. Let's get everybody together. Bertrand, forget about configuration management. Let's try to think, how do we specify the systems to begin with so that we can develop these systems in a rational way. Methods, tools, and techniques, which have been our mantra for, 20 to 30 years. And we'll leave it all at that, and that's all we had to show today.
Brilliant.
Thank you.
Well, I've chaired a couple of sessions and I haven't asked a question, so I want to ask the first question, if I may, while you're thinking of yours. When one moves to the cloud, as you've done so successfully with real-life applications like this, what is the requirement on the use of the internet? Because that's a question I was asked down in Africa. When people wanted to switch from a supercomputer to the cloud, they said, oops, but we don't actually have the internet capacity.
We don't have it yet. We're abstracting on that, and this is a very relevant question to Brazil because broadband is really a problem.
Right.
We're abstracting on that in the sense that we're thinking that in 2 years or 3 years, we cannot advance software engineering research so quickly. So by the time we have solutions that will optimize that, and that's what Anuth said, you know what, don't optimize your computer, your algorithm, buy new computers. By the time we're done with that, we'll have a newer infrastructure, and I think this is going to happen in the next 2 to 5 years. Optical cables, we're renewing it systematically.
So you currently have the problem?
We do have, yes, definitely. So by using Amazon or Azure, and I think Azure, Mintis is promising me that they are going to have cloud edges in Brazil and South America because none of the big providers do so far. They don't have it. So uploading those videos to a cloud provider is not good, and Microsoft could go forward and just start doing that and do it geographically divided. We have continental dimensions, and having your cloud provider provide, machines in strategic geographic locations will make a huge difference for these applications, definitely.
Okay. Okay, so now over to you. Yes.
So I was wondering, in the split up and merge approach, what kind of codec videos you can support and what codec are left out?
So basically, we are using the M-coder or FFmpeg, so it supports the range of. We actually are using the A.264 for video encoding, and the input file is named JPEG with high definition.
But since we are using third-party projects to do the actual transcoding, it doesn't matter. It's important, but in the input view, that you might be able to identify the keyframes because that's important for the
Yes.
Excuse me, you're talking about encoding via the cloud. Is it any possible to think about decoding via the cloud? Is it necessary?
Well, I would say the main problem with decoding is usually when you're decoding content. It usually means that you're going to reproduce this content on a video screen and then the overhead of decoding that on the cloud and then transferring it to the video screen wouldn't make it wouldn't be worth it right now due to bandwidth problems. To encode it, usually you don't usually have that time frame. You can usually do it even offline. So for instance, in these videos, for the selection process, we could send it to the cloud and have them transcoded, even if we took more time, and it wouldn't be such a problem. But if you're decoding it, you probably want to display it in the screen. And once you have it uncompressed, to transfer it from the cloud to your screen will be a huge problem.
Mm-hmm. Okay, well, I think that leaves us all 10 minutes to go and get coffee and cakes, which was my objective. And then we have to assemble over there for the closing session in the big room. Thank you very much.